Hello everyone. Now we're going to be going over section 6.5, which is on graphs of the tangent, cotangent, cosecant, and secant functions. So we have four objectives today, one being that we want to graph the tangent function y is equal to tangent of x, and the cotangent function y is equal to cotangent of x. Two, graph functions of the form y is equal to a tangent of omega x plus b, and y is equal to a cotangent omega x plus b. 3, graph the cosecant function y is equal to cosecant x and the secant function y is equal to secant of x. And 4, graph functions of the form y is equal to a cosecant of omega x plus b and y is equal to a secant of omega x plus b. So, all right, starting with objective 1, we want to graph the tangent function y is equal to tangent of x and the cotangent function y is equal to cotangent of x. So since the tangent function has a period of pi, which is unlike sine, cosine, cosecant, or secant, which they all have periods of 2 pi, tangent and cotangent will have a period of just pi. So we only need to determine the graph over some interval of length pi instead of 2 pi. But the tangent function is not defined at certain values. So the tangent function itself is not defined at negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so on. We can concentrate just on the interval negative pi over 2 to pi over 2 for length pi. So then we can use key points to construct our curve. So we have our tangent curve here. We also have our summary table with all of these same values. Once again, this is found in your book as well. So we have our graph here of y is equal to tangent of x. So we see we have our function undefined at negative pi over 2 and positive pi over 2. So what that means is that we have vertical asymptotes at those points. So we can't draw any points on them. So we can signify this by just writing some red dashed lines. And then we see that our function is going to start on the positive end, increasing up towards infinity, but never reaching pi over 2. And on our negative end, going down to negative infinity, but never reaching negative pi over 2. Then we see important points here would be at negative pi over 3, square root of negative square root of 3, negative pi over 4, negative 1, negative 6, negative pi over 6, negative square root of 3 over 3, 0, 0, pi over 6, square root of 3 over 3, pi over 4, 1, pi over 3, square root of 3. So we have our important points here. We see tangent kind of moves in this specific direction. We see it moving in this direction here. So a few things, we can notice that tangent is once again not defined on negative pi over 2 or pi over 2. So even though these are endpoints, so that's why we draw these vertical asymptotes, which we represent just by our red dashed lines. So then that's how we see that if pi over 2, or if x is close to pi over 2 but not quite pi over 2, then sine of x is close to 1 and cosine of x is close to 0. This is how we end up getting our positive infinity. That just means that as x approaches pi over 2, we see that tangent of x approaches infinity. And so we get this because tangent of x we know is represented by sine of x divided by cosine of x. So what we're seeing is that sine of x is almost 1 and cosine of x is an incredibly small number, which would then create positive infinity. So similar thing goes for as approaching negative pi over 2. So negative pi over 2, but more than negative pi over 2, then sine of x is close to negative 1 and cosine of x is once again close to 0. So then we see tangent of x is equal to sine of x over cosine of x, so we get that negative infinity. So with these observations, if we looked at y is equal to tangent of x over multiple periods, this is what we would end up seeing. So we see we have many vertical asymptotes. We see negative 5 pi over 2, negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, so on. So we see we have our many vertical asymptotes. Our different functions of tangent of x are passing through negative 2 pi, pi, 0, pi, 2 pi. So we see that our tangent of x naturally passes through the x-axis at integer multiples of pi. Then we see at the points negative pi over 4 and pi over 4, we cross through our point -1 or +1. So those are our main attributes there for our different graphs of tangent of x over multiple periods. So it's always good to focus on your one period. So most often going to be some variation of negative pi over 2 to pi over 2. But then you can also graph more periods as well once you get the main kind of shape of your graph down. So then here are the following properties of y is equal to tangent of x. So the domain is the set of all real numbers except odd multiples of pi over 2. The range is a set of all real numbers, so the range is all real numbers. Tangent function is an odd function, so symmetry of the graph with respect to the origin. The tangent function is periodic with period of just pi. X-intercepts are going to be -2 pi, -pi, 0 pi, 2 pi, 3 pi. Y-intercept ends up being 0. Vertical asymptotes will then occur at x equals -3 pi over 2, -pi over 2, pi over 2, 3 pi over 2, and so on. So these are properties of tangent. And we know that cotangent is the reciprocal of tangent. So if cotangent is reciprocal of tangent, what we're going to see is that the graph of cotangent is going to be obtained the same way as the graph of tangent. So we see that cotangent now is not defined for integer multiples of pi. So important intervals would then be -pi to 0, 0 to pi, pi to 2 pi, etc. So just like tangent, cotangent has vertical asymptotes at integer multiples of pi. Then in the intervals 0 to pi, if x is close to 0 but slightly larger, then cosine of x is close to 1 and sine of x is close to 0. So this means that as x approaches 0, we're going to see that our graph is going to go towards infinity. Then as x approaches pi, our graph will end up going towards negative infinity. So those are our main differences between tangent and cotangent there. So then if we graphed cotangent over many periods, we'll get this image here. Once again, we have our summary table with all of these important values. But here we see our many graphs of cotangent over different periods. So we see our vertical asymptotes there at -2 pi, -pi, 0 pi, 2 pi, and so on. Then we see that our graphs of cotangent are passing through the x-axis. So our graphs of cotangent equals 0 when x is -3 pi over 2, -pi over 2, +pi over 2, 3 pi over 2, 5 pi over 2. Then lastly, important points are then going to be then divided by 4. So those integer multiples of pi over 4. So then we'd be looking at pi over 4 and 3 pi over 4. And those are important points because that would be when the graph of cotangent or y equals cotangent of pi over 4 would then be equal to 1. So all right, this kind of gives us an idea of the difference between cotangent and tangent. So we really see that they're very similar. The only thing is that cotangent is flipped and they reside on different intervals. But other than that, they are very similar. So now moving on to objective 2, we want to graph functions of the form y is equal to a tangent of omega x and y is equal to a cotangent of omega x plus b. Oh, I missed that plus b on that last objective. But anywho, so for tangent functions, so whenever we say tangent functions, we're referring to tangent and cotangent functions. There is no concept of amplitude since their range is -infinity to infinity. So really the only role of a, or the value of a, is going to be to measure the vertical stretch, and the period of tangent is also pi. So when we see our equation here, y is equal to a tangent of omega x plus b, the period of our graph would then be pi over omega. So our range for these functions are always going to be negative infinity to infinity, but that a is just estimating our vertical stretch that we have there. So then lastly, b just indicates a vertical shift. So once again, we're going to go ahead and do these problems by graphing by using key points. So remember, those were our 4 steps. So we factor in that vertical shift at around step 3 when we find the y values in our key points. So all right, for our first example, we want to graph y is equal to 3 cotangent of 2x minus 1 and then determine the domain and the range. So we have our graph here, but it's not marked or anything, so we'll have to mark it up ourselves. But we given our equation, and we want to use the 4 steps we use when using key points to graph a specific kind of function. So we're going to use those steps. So in step 1, remember we want to find the amplitude and the period of the function. So step 1, we get amplitude. It's going to be 3, or the absolute value of 3, which is just 3. Then our period is pi divided by omega, which in this case, omega is 2. So in this case, our period is going to be pi over 2. So what we're going to see is that we're going to see that horizontal compression. We're now taking all of our important points, dividing them by 2. So step 2, now remember we want to create those 4 subintervals. So we take our period and we divide by 4. So our period was pi over 2. We're dividing by 4, and this means that we need to separate out our subintervals to each be of length pi over 8. So in this case, for pi over 8, we're going to see our intervals end up being 0 to pi over 8. Pi over 8 to pi over 4. Pi over 4 to 3 pi over 8. Oh, wrong one. 3 pi over 8. 3 pi over 8 to lastly pi over 2. So these are the proposed subintervals. So what we see here is that when we move on to step 3, and we're going to move to step 3 down here. Using our subintervals, we can go ahead and say that our x values of our key points would then be 0, pi over 8, pi over 4, 3 pi over 8, and pi over 2. These would be our x values, but what we see is that our function is not defined at x equals 0 or pi over 2. So that signifies our period, or the endpoints of our period. So when we have our subintervals, really what we're considering is not 0 and not pi over 2, but all values in between. So if our function is not defined at x equals 0 or pi over 2, that means that when we find our y values, we're just finding y values for pi over 8, pi over 4, and 3 pi over 8. That kind of looks like a 6. There we go. So let's go ahead and find our y values. So for our y values, our equation was given to us as y is equal to 3 cotangent of 2x minus 1. And our first x value is going to be pi over 8. So this is going to simplify to 3 cotangent of pi over 4 minus 1, which in this case, cotangent of pi over 4 is going to be 1. So we have 3 times 1 minus 1, which is 2. So this means that our first key point is pi over 8 comma 2. Now for our next value, we have 3 cotangent of 2 times pi over 4 minus 1. So this is 3 cotangent of pi over 2 minus 1. So cotangent of pi over 2 is going to be 0, so that's just 3 times 0, which is 0. So 0 minus 1 is negative 1, which tells us our point, pi over 4, negative 1. Then our last value that we're estimating here, or finding here, is 3 cotangent of 2 times 3 pi over 8 minus 1. This gives us 3 cotangent of 3 pi over 4 minus 1 is going to then be equal to 3 times negative 1. So cotangent of 3 pi over 4 is negative 1. So 3 times negative 1 minus 1 is going to then be equal to negative 4. So then 3 pi over 8 and negative 4. So these are going to be our key points. Let's go ahead and highlight those in blue. So these are our key points. Let's go ahead and mark up our graph. So for our y-axis, we'll go ahead and say that this is going to be 1, 2, 3, 1, 2, 3. Then on our x-axis, we'll make marks on every notch here. And we'll say that this first one is going to be pi over 8, then pi over 4, then 3 pi over 8, and pi over 2. And so when we graph this, we're going to go ahead and graph 2 periods. We're going to graph one using our key points, and then graph in our next period over by using our first graph. So then in our next graph here, we'll end up with 5 pi over 8, 3 pi over 4, 7 pi over 8, and then pi. So our function is not going to be defined at x equals 0, pi halves, or pi. So we can go ahead and draw in some vertical asymptotes. So this is 0, pi halves, and pi. So these are our vertical asymptotes. So now we can go ahead and plot our actual points. So focusing on our first period, 0 to pi halves, we're going to go ahead and plot our key points. So our first key point being pi over 8 and 2. So we have pi over 8 to 2. Then we have pi over 4, negative 1. And then we have 3 pi over 8, negative 4. Oh, okay, so our graph doesn't reach down to negative 4, so let's go ahead and fix that. Let's grab this one and pull down to about here. There we go. All right. So 3 pi over 8, -4. So these are our points here. And so what we see is that as x approaches 0, our function is going to go to positive infinity. And as our function approaches pi over 2, our function will continue on to negative infinity. So that being said, let's go ahead and just connect our 3 points and then draw the rest. So between our 3 points, our function is going to end up looking like this. And from there, we know that our functions will continue on to go towards infinity and negative infinity. And we join our arrows, and that completes our graph of our tangent function between our first period 0 and pi over 2. Now let's just go ahead and complete our next period, which should be fairly straightforward based on our first one. We just essentially want to copy over these key points and copy this graph over to our next period. So in our next period, we're going to have key points of 5 pi over 8 and 2, 3 pi over 4, and -1. Let's scoot this over a little bit up and grab all of it. There we go. Scoot that over a little bit so we have some room. 3 pi over 4, -1. And 7 pi over 8, -4. This is going to be super in the way. So let's move it to the other side. There we go. So we've essentially just copied over the same graph to our next period. And so we do the same thing as before. We connect our points, and then we draw the rest of our graph in. So we see this is what our graph of y is equal to 3 cotangent of 2x minus 1 is going to look like over 2 different periods. So all right, we've completed our 4 steps. Now the last thing I want to do is determine the domain and the range. So as we went over, all tangent functions have a range of negative infinity to infinity or all real numbers. So we can go ahead and write that in. We'll write our domain probably first, so we'll say our range is all real numbers. Another way we can signify all real numbers is by just writing negative infinity to infinity if you don't want to write out all real numbers. Then our domain is going to be a little bit different than normal. So our domain is going to be fairly specific. Our domain is going to be, not 0, not pi over 2, not pi. So we have to not consider integer multiples of pi over 2. Our domain will exist everywhere, not on an integer multiple of pi over 2. So we need to find a way to write that out. And how we're going to do this is we're going to express our domain in set builder notation. So that's what this is going to be called. And all we use is that we use curly brackets. We state our domain, which is x. So we say our domain is x, and then we have to list a property. So we're going to draw this vertical line after the x, and then we'll write out our property. Our property doesn't have to be very long, it can be pretty short. And what ours is going to be is that we know that we want to write something along the lines of x exists everywhere where it is not an integer multiple of pi over 2. That's quite a bit to write, so we're going to write it a little bit shorter. So we write our domain is x, where x is not equal to, so this is the not equal to sign, x is not equal to, and now we're going to write k pi over 2, and now we just have to state what k is. So we're saying that x is k pi over 2, and we're going to move this around a little bit so that we have some room to write this out. So we're going to move our range lower. I'm going to write it right there. Erase that. So x is not equal to k pi over 2 when k is an integer. And that ends our set builder notation. So we use set builder notation when we kind of have these specific domains like this, because we don't want to write out each and every interval, because that goes on for infinity. But we want to make sure that we get an accurate answer. So this is how we use set builder notation, where we say our domain is X. We write that vertical line and then we state our property of X. So we say X where X is not equal to K pi over 2, where K is an integer. And then our range is all round numbers. So that there would be our domain and range of our cotangent function that we were given.